Hello and welcome to I Know Dino. I'm Garrett.
And I'm Sabrina.
And today in our 417th episode, we have a ton of dinosaur news stories from SVP.
Oh yes, we are continuing the coverage.
And there is no interview this week, which means there's even more SVP stuff we're going to be covering. It's mostly on the Dinosaur Macroecology and Macroevolution session, but we also have some stuff from the Theropod and also the Taphonomy sessions.
Oh yeah.
Which were really great. Also, we have Dinosaur of the Day, Caenagnathus or Caenagnathus.
Depending on your preference.
Yeah, we heard a lot of Caenagnathus at SVP this year. And some of our SVP talks actually relate to Caenagnathus. So you can look forward to that.
And whichever pronunciation we decide to do.
Might flip back and forth. But before we get into all of that, we want to thank some of our patrons for helping to keep the podcast running and helping to support us getting to SVP and covering all this good stuff. And this week, we'd like to thank Kyle, the Georges family, Anne, Greg, Reed, Lawrence, Burnsasaurus, Saskisaurus, Jackson Crawford, and Ankylosaurus.
Yay, thank you so much for being part of our community and supporting the show. It means a lot to both of us.
So without further ado, because we have a lot of SVP stuff to talk about, we're going to jump into our Dinosaur Macroecology and Macroevolution talks. And as you can tell from that topic, it's mostly about things relating to how dinosaurs evolved and what was going on in their environments. But it kind of spills over because all the sessions that are about dinosaurs get a little bit of other stuff mixed in because we just can't resist.
Oh, I was thinking because you can connect so many things.
That's true too. So up first, we had a talk by Gardner, and they were looking at basically the idea of how fast do animals evolve new movements. So you can think of something like flight or walking or running. And in order to do any of those motions, you need certain body adaptations. Like obviously a fish can't walk. So what does it need in order to walk? It has to grow limbs. The fins have to change in major ways, all that kind of stuff. So with dinosaurs, there are multiple ways that things change because the very earliest dinosaurs were bipedal, but they might not have been as fast as they could have been. So over time, some of them evolved different adaptations to run faster. Then you have other dinosaurs that were evolving quadrupedality. So how did their arms need to change in order to support their weight? And then finally, as we all know, dinosaurs evolved into birds, the last remaining form of dinosaurs around today. And so they had to evolve their arms into wings. So there's a lot of different adaptations that went on for animal movement in dinosaurs. So to get at how these different dinosaurs changed over time and sort of quantifying which dinosaurs were ready to run, were ready to walk quadrupedally, were ready to fly, they were mostly looking at the leverage, basically, of these limbs, and they would quantify it into a term that they called the gear ratio, which is basically the limb length divided by the moment arm, but you can think of it like a gear ratio in a car, basically the length of the motion divided by the strength of the muscle. So, in other words, cheetahs have really long strides and relatively weaker muscles, so they have a high gear ratio. But that's really good for high speeds, just like a high gear ratio in a car, if you're familiar with.
Ah, I see.
Elephants, on the other hand, have really short strides, but very strong muscles. So they're on the opposite end of the spectrum. They have a very low gear ratio. There's like a lot of torque, basically. They can get a lot of mass moving at low speed, but since they don't have that high gear ratio, they can't get going all that quickly. Although faster than a lot of people expect. You don't really want to be running away from an elephant. They can go pretty quick.
Yep. Don't underestimate an elephant.
No. Yeah, not as fast as a cheetah, which you're definitely not outrunning, but an elephant can, still cause some damage. So they looked at 31 ornithischians, 9 sauropodomorphs, and 62 theropods. Theropods often are the ones with the most sampling because we have so many birds. Like we've got like 10,000. So you can have like 10,000 theropods in your sample if you really wanted to. What they found is that dinosaurs switched from tail-driven motion with the caudofemoralis muscle basically lifting the leg. That's the muscle that goes up the leg, the back of the leg, and then down the tail. So as they swing the tail from side to side, it helps them walk. That's what early dinosaurs were doing. And over time, a lot of them switched to a knee-driven walking, which is a little bit more analogous to what we do, obviously, because we don't have a tail to help us walk. But they have a specific muscle I don't think we've mentioned before, so I'll just mention it in case you're curious. It's called the iliotibialis lateralis post-acetabular. So that tells you basically where it connects on the tibia and then where it connects on the acetabulum. So yeah, that's the knee is doing the bending there. I guess kind of like our hamstring probably would be the closest thing you could compare it to. And that allowed them to use, their hip and their knee to like extend their leg rather than relying on the tail so much. So that doesn't seem like a huge change. It's like, okay, well, they switched from using their tail to using this muscle in their leg, but it's still doing basically the same thing. Why is that important? Well, when you're evolving flight later on as a bird, you can't have this big, heavy tail hanging off the back.
Weighing you down?
Exactly. They needed a different form of motion, which didn't rely on this big tail sticking out the back. Plus, it allows the whole sort of system to shrink down even more because then it's all just contained in that leg and the leg can shrink down and they can focus more on the arm growth. They did find a couple of outliers in terms of how fast the gear ratio, as they call it, was changing in different dinosaurs. Most of the higher rates of evolution were in the Maniraptoran dinosaurs. That's the group that's turning into birds. But there were a couple of other interesting outliers, like Liaoningosaurus, a juvenile ankylosaur, also had a really high rate of change. And they think it could be related to quadrupedality, or maybe it's ontogeny because it was a young one. So maybe there was something weird about its gear ratio, but it would have changed as it grew up, and maybe it wasn't all that weird overall. But we don't have an adult to compare to, so it's hard to say. They didn't see any noticeable faster evolution in any groups for the forelimbs, which is pretty interesting because when thinking about the most impressive thing dinosaurs did, turning into birds seemed like one of the big ones that it would be.
Mm-hmm.
But outside of that, Maniraptoran dinosaurs and their legs, they didn't see it in the other side. But as I was saying, that switch from tail-driven to leg-driven could cause some pretty big changes in the legs, which I never really thought about before. Like how did the legs change in order to evolve flight is a really interesting question because it's so easy to focus on the wings. That means that on average, the hind limbs evolved faster than the forelimbs, even in these dinosaurs that evolved flight. And again, it was really important for those hind limbs to change a lot in order to allow flight.
Yeah.
It's a pretty cool study. I'm very curious to see if anybody digs more into that Liaoningosaurus, the juvenile ankylosaur, because I'd be very curious to see if there was something going on there. Like, what if it's evolving bipedality again?
Ooh.
Or it was bipedal as a baby and was evolving, or as it grew up, became a quadruped or something like that. It just would be really interesting to see.
That would be interesting. There were a lot of talks about theropods, which, Gary, like you mentioned, there's a lot of theropod specimens. Maybe that's why. But theropods are also, in general, pretty popular.
And specifically, a lot of talks about T-Rex arms this session, which was kind of weird.
Well, not just T-Rex, right? Tyrannosaur.
Oh, true. Yeah. I think the reason people are interested in Tyrannosaur arms is because of T-Rex.
Yeah.
But yeah, we have very few T-Rex arms, so you have to work with a lot of other Tyrannosaurs.
So Funston presented on Tyrannosaur arms getting shorter.
As we know they did.
Yes. And looked at what might be linked to that. Because a lot of times we talk about, well, maybe Tyrannosaurs had small arms because it was compensating for their large heads or their large body sizes. Now, what they did was they plotted a bunch of femur and humerus lengths, so arm and legs, and they found that similarly sized tyrannosauroids had different arm lengths. And there was this drastic change in one early clade, starting with Dryptosaurus. And Dryptosaurus is closely related to Tyrannosaurus and Tarbosaurus and those really famous tyrannosaurs.
So in other words, it wasn't just how big the tyrannosaur was determining how small its arm was. It was a specific group of tyrannosaurs that sort of went their own way with arms shrinking.
And it looked like that happened early on in Tyrannosaur evolution and probably earlier than other parts of their body plans. So it was something It's like one of their first things to happen.
Yeah.
But they did mention there's missing data and fossils. You just need more of that to help confirm this.
Yeah, because even though we have more arms from other tyrannosaurs, we still don't have that many tyrannosaur arms to work from.
Yeah. But it's interesting to think about, like maybe these features, like the short arms, helped them become big once there was an opportunity to ecologically.
Yeah, very true. Yeah, it's really interesting because I think we pretty much always say the reason tyrannosaurs had tiny arms was because they had a huge head, and it's a balance thing, and also they don't need arms anymore. Imagine how big their arms would have to be useful for them, and then but they already have such a good mouth. Why would they need that? So yeah, it's interesting to hear that even before they got that big, a lot of them had smaller arms.
Yeah. What was the advantage?
Yeah. They didn't pose an answer to that question.
I'm sure there'll be future studies.
Yeah. And it's also one of those good examples of, even though a lot of early tyrannosaurs did have bigger arms, you have to look at it in terms of which ones evolved into which, segmented a little bit more. You can't just look at all tyrannosaurs and say, oh, the early ones had bigger arms and the later ones had smaller arms, relatively speaking, because if you can look at the specific lineage, you might see something a little different. It was pretty funny because Tom Holtz went up shortly after this and pointed out that even though other people are talking about tyrannosaurs, he for once was not talking about tyrannosaurs.
Yeah, we teased this one in our Twitter.
So basically, for the last couple of years at SVP, Tom has been talking about different groups of dinosaurs and where they fit in a morphospace, basically, or with principal component analysis. What that means is basically you're trying to plot some features of different animals and then see where they group out together. And that might tell you things, for example, like if there's a dinosaur and you're not sure what it ate, but when you plot it against other dinosaurs in this space and it ends up looking a lot like, or in the same space as the herbivores, you'd think, okay, maybe that was an herbivore. And you don't necessarily have to go through and say, okay, well, it's got this tooth that looks slightly more herbivorous and try to weigh it yourself. You can let the computer do it, is essentially what it is. It's very limited in terms of its power to what inputs you give it. So you have to decide what measurements it's going to be, like jaw length, size of the tooth, whether or not it has serrations, all of these kinds of things. And then the computer will figure out which of those features best groups these animals together or best explains the differences between them. So what he was doing this year was looking at expanding from carnivores, which last year he found that there were two sorts of different groups of carnivores, the ones that were handy versus bitey, as they put it.
Yep.
So obviously Tyrannosaurus is going to be a bitey one, but then you've got some other dinosaurs, maybe an Allosaurus that has more hands action going on.
More hands-on approach.
Exactly. So that was the one axis on the scale. The other axis was size. So ended up with, the small ones are doing something different. And then we've got the ones with big hands versus big mouths. And they're not always the same, right? You've got stuff like alvarsaurids, which are very bitey, not so much handy. So this year, they're expanding that analysis to things that don't eat vertebrates, as he put it. In other words, they're eating either plants or insects, because there is a pretty big difference between the type of adaptations you have if you're hunting another dinosaur or a mammal or something like that versus eating ants or beetles or something. It might be a little bit more analogous to an herbivore. You can't really tell until you do the analysis. So they added in a ton of species. They're up to 121 species of dinosaurs, as well as 4 juvenile tyrannosaurids, because even though it wasn't about tyrannosaurs, you can't resist because he's Tom Holtz. He's one of the tyrannosaur guys. In general, the non-carnivores did come out in an area on the opposite side from the carnivores. So one of the axes seemed to shift over into like the trophic level, basically, whether they're eating either vertebrates or something that is a plant or just ate a plant. But unfortunately, he was saying there were some flaws, he thinks, in his methods. So he pulled out the results. I was like, I'm going to redo this, which was really cool to see because it's a good example of the scientific method. He showed it to some other scientists. They were like, yeah, you might want to rework this. And so he's going to, and we'll get better results later.
Yep.
But I did really enjoy the rehashing of the bitey versus handy.
Yeah. Catchy phrase.
Yeah. And it could be really useful, this sort of analysis in the future, because sometimes you just get a small bone of an animal and it's really hard to tell what it came from. But it would be useful if you could at least say, oh, that's an herbivore type shape of a jaw or something like that.
Going back to the carnivorous theropods, because why not? Schroeder gave a talk about niche partitioning, so different types of theropods that lived alongside each other. If you look at modern animals, competition for food leads to low population. For example, wild dogs compete with hyenas and lions for food, and there's a low population of wild dogs.
Yeah, so basically in the areas where you have the big carnivores like lions, there are way less dogs than if you have an area without the lions.
Yes. And they were looking at medium-sized carnivorous dinosaurs. Many of them are paravians. And there's a lot of diversity in paravians, likely due to the small body size, the light bones, having the feathers. There was a good question that if small paravians are successful, then why did some of them get big? Why mess with that success?
And how big could they get when there were other larger theropods in that environment?
Yeah, exactly. And how could they get along with them and live alongside them? And it could be because of their pre-flight adaptations. Now, being bigger doesn't necessarily mean that they were a better runner. And I'll backtrack a little bit with how fast you run increases with body size up to a point. They found that paravians that weighed over 30 kilograms were significantly slower than expected for their size. They hit a plateau in their max running speeds. So you can't simply scale up your expectations for running speeds, like just saying, oh, that's larger, so it must have been a faster runner. So looking more closely into that, you can look at the amount of energy that's spent when running, and they found two different styles for running and energy. There's the fast and inefficient way, or the slow and efficient way.
Yeah, they called the fast, inefficient ones the cheetahs, and the slow but efficient ones the marathoners.
Yeah.
Which is a pretty good way to look at it.
Yes.
Humans are very much the marathoner style, in case you're curious.
Yeah.
There's this group in Africa that like basically chases animals to death over like dozens of miles. So if you ever need to hunt and you're in the wilderness, we're marathoners, just so you know.
Don't do it the cheetah way.
No, it doesn't work for humans.
Cheetahs come up a lot in these studies.
They do. They're such an extreme end of the spectrum, and everybody knows what cheetahs are like.
Mm-hmm. So back to the dinosaurs, the small paravians, the ones that weigh under 30 kilograms, they're relatively quick. They could probably run for a short period of time to catch their prey.
So they're the cheetahs.
Yeah, they're the cheetahs. And the big ones, those are the marathon runners, the efficient runners. And there's overlap between the large paravians and their running abilities with megatheropods.
So that means there was probably a lot of competition between the two if they're using the same sort of hunting style.
Yes. And then that goes back to, well, when you've got the megatheropods and the giant paravians, there's going to be fewer of those paravians around because they're going after the same prey in a similar style.
And specifically, too, there's that subset of megatheropods that are still growing up and might be causing problems. But this was really looking at just megatheropods on their own might be enough, even without the juveniles in the mix, to sort of scare off the larger paravians.
Now, it's possible that those larger paravians, similar to what African wild dogs do, where they have, there's fewer of them around because they're in competition with these other large carnivores, maybe the giant paravians traveled long distances to avoid kleptoparasitism, meaning they avoided the competition while still living alongside them.
Yeah, I really liked the term kleptoparasitism. I get it's like sort of like kleptomania.
Yeah.
But in this case, it's more like you hunt something, you kill it, you're about to eat it, and then the big guy comes over and is like, I'll take that now.
Yeah.
So you got to try to stay away from them. You could see how that's not a real winning strategy.
No, it takes a lot of energy to get that prey.
Yeah. And then even if you can't end up eating it, that's a tough life.
Mm-hmm.
And that's why most of the paravians stayed smaller, potentially.
Still doesn't answer the question, why did some of them get big?
Yeah. That was also one of the talks where they hinted at maybe Dakotaraptor isn't valid because that is a large paravian, basically at the upper end of the scale that you probably wouldn't expect to find, maybe. So the jury's still out on that. I don't think anything's been published trying to retract Dakotaraptor yet.
No, and there were definitely at least posters that mentioned Dakotaraptor at SVP.
Yeah. Well, one of the hypotheses now is that it might be a chimera, like some bones from some animal and some bones from another. At least some of them are probably, I mean, they're all real bones, right? So if there's a huge claw there, it might indicate that there was a larger raptor.
Belonged to something.
Yeah, exactly. So those are all the talks we have from the Dinosaur Macroecology and Macroevolution session. And up next, we've got a bunch of talks about dinosaur soft tissues and taphonomy, but first we're going to pause for a quick sponsor break.
Onto the soft tissues and taphonomy.
Oh, yeah. Yeah, got to get to the real exciting stuff. Sorry, macroecology people. We love taphonomy.
Oh, there were interesting talks.
There were.
There's just something about soft tissues, too.
There is, yeah. And that very first step in fossilization, which is the bodies decaying and changing and everything. So interesting. So the first talk we have here was by Serio, and they were looking at nictitating membranes.
You love saying that word.
It's such a cool thing. So nictitating membranes, if you're not familiar, are a inner eyelid, which a lot of animals have. Humans don't have them. I think in general, mammals don't have them, but frogs, most amniotes, amphibians all have them, while lizards are missing them. And birds, interestingly, are missing some of the muscles that all the other animals that have nictitating membranes use, but they still have nictitating membranes.
They figured out how to do more with less.
Exactly. Yeah, so there's something weird going on there. And the really cool thing about it is that they basically could look at some of the different bumps on the bones around eye sockets and look into how these muscles would have attached in dinosaurs. So they can look for like eye muscles by little tiny clues around the eye socket, which is just such an amazing thing that they could even do this.
Yeah.
So if you're not familiar, so nictitating membranes are useful just like our eyelids are when we blink. It maintains the tear film for our optics, which I thought was such an interesting way to describe it. Like we need a tear film over our eyes, and so do other animals that have eyes. So really cool. Birds, it turns out, only have 2 nictitating muscles, and they're a little bit different than other dinosaurs. What they found is that Majungasaurus still appears to have this retractor muscle, which is lost in birds. So that's one that was more like the other normal way of having eye muscles if you have a nictitating membrane.
Or just another way Majungasaurus wasn't quite as bird-like.
Yeah, exactly. Dromaeosaurus also has a site for that retractor muscle, and that one specifically looks similar to turtles, apparently.
Another animal that pops up a lot. Cheetahs and turtles.
Yes. However, Archaeopteryx doesn't have any obvious muscle attachment point for this retractor muscle. That's the one that got lost in birds. Although there was a small piece of the best example fossil missing where it could have maybe been, because they're not always, the muscle attachment points aren't always in the exact same spots. It can move around a little bit, but you can tell relative to where it is, like which side of the socket it's on in general, what the purpose of that muscle is, because, you know, it can only pull in the direction that it's in. So it's possible it had it, but probably not. And then we can tell that enantiornithines didn't have the retractor muscles. So the conclusion is that dinosaurs had eyeball retractor muscles, but the earliest birds didn't have them. And then again, even some of the larger dinosaurs, which were sort of getting closer related to birds, like Majungasaurus, because that's on the vaguely bird lineage, also still had them. So it might have been lost, this muscle, because of the miniaturization of the head that we see in birds.
Right.
But when the dinosaurs miniaturized their heads, they maintained really big eyes. So basically, there wasn't any room left in the head for these extra muscles. So they had to, like you said, do more with less.
Yeah. Maybe that gave them an advantage somehow.
Yeah. They gave a cool example, too, of the ostrich and how their eyes completely fill the orbit. So there isn't really much room around them.
They do have large eyes.
Apparently, they have, I think they said the largest eyes on land.
Whoa.
The ostrich, and they're not even close to the largest animals. So yeah, they definitely managed to shrink their head way down, and they have tiny heads with really big eyes.
They do look a bit cartoonish.
Yeah. So I just thought that was really cool. I love hearing about nictitating membranes, and I can't believe that we can tell whether a dinosaur had a nictitating membrane.
Yeah.
And, how its eye musculature looked from fossils. That's just amazing.
So many cool details.
There was also an interesting talk by Jessica O'Neill looking at a totally different topic, which was basically, could we do the same type of analysis on fossils, looking at specifically the chemistry of the fossils in a non-destructive way rather than a destructive way, and get similar results, like a similar level of accuracy? Because a lot of times, in order to get accurate results, you gotta, when you're doing the chemistry of a fossil, sort of cut out a chunk, grind it up, throw it into an ICP-MS, which is a mass spectrometer, and then get your results out of it. But the ICP-MS, you obviously have to destroy the sample in order to do that, so people don't want to do that.
Mm-hmm.
There is something called XRF, which is basically like a fancy X-ray scanner, and obviously that's not destructive, or it can be much less destructive. There is like a version that's a little bit destructive, but not as destructive as ICP-MS. So really, the less destruction you can do, the better. The really interesting thing, though, to me, was that what they found was that it depended on the chemical whether or not it was better. So the non-destructive test did pretty well with manganese, and it did okay with, I think, strontium. But for some of the other metals that they tested, it didn't do as well. So I guess it means that the researchers have to be a little bit more precise about the questions they're going to ask and figure out, okay, well, I only really need to know about these metals. Maybe I can get away without doing destructive testing, which is pretty handy, because a lot of times we hear about how people want to do destructive testing and they can't get approved for it.
Yeah, if there's a way around it.
Yeah, depending on which question you're asking, at least. Next up was a really cool presentation by Von Strum, and they were basically talking about what may be the earliest theropod embryos ever discovered.
I like the title of this one. It started off with scrambled eggs.
Yeah, because this is another example of embryos in an egg that are somehow like completely messed up, but still somehow preserved. Like these tiny, delicate bones got preserved for millions of years, and yet also got broken into bits.
How does that even happen?
It's so weird. So basically what they found was in the early Jurassic, some dinosaur eggs, and they think that they're from theropods because they did some synchrotron scanning, which is that super high power X-ray, using that like basically like particle accelerator for a really high power X-ray beam. And they found some really tiny, like less than 5 millimeter teeth, which look like they're probably theropod teeth. Although weirdly, those teeth are mostly in isolation. They're not like in the upper or lower jaw or anything.
It's part of the scramble.
It's a pretty extreme scramble. All the teeth got like obliterated out of the bones that they were in. And then there's also a shell that's relatively thick with what looks like maybe a medullary layer, which is typical for a theropod. They also found what they think are palatal teeth, and that means teeth on the roof of the mouth, which is pretty crazy, although apparently it's been seen in a couple other dinosaurs. It's really common in other vertebrates in general, like mosasaurs. They showed that in Jurassic World, how it has a bunch of teeth on the roof of its mouth. It's crazy to think about, but yeah, a lot of animals have teeth in all sorts of spaces. They can be useful in all parts of the mouth. They also found a few osteoderms and potentially some soft tissue, which could be skin, and then likely some scales are in the mix too. So if all of these details are correct, we might have a theropod with osteoderms and teeth on its palate. But it did sort of make a lot of the audience wonder, is that really a theropod? Since those are kind of weird features for a theropod.
Yep.
It also seemed to have some fusion in its vertebrae at the end of the tail, which is a little bit unusual. Although some dinosaurs do have that. It might be a little unusual for an embryo. We don't have a ton of examples to compare to, though. So one competing hypothesis that was sort of growing in the audience was that it could be a pseudosuchian, because pseudosuchians obviously have osteoderms. They also have pretty similar teeth, and crocodilians in general sort of fuse from their tip of their tail forward. So that's possible that it was, but the answer to that was basically the area that this is in is really dinosaur dominated. There's tons of dinosaur tracks everywhere. We don't really see much in the way of pseudosuchians. We're in the early Jurassic. We're not in the Triassic. So dinosaurs have pretty well taken over at this point. And the bones look in general to look like dinosaurs. He didn't really get into a lot of details of the bones themselves because it's still being worked on. But yeah, it'll be interesting to see. Either way, it's a really cool embryo from the early Jurassic.
Yeah.
And it was actually kind of funny because a few of the slides were clicked over to them to show some really pretty image. Like the slide didn't work.
Oh, yeah, I
So
remember.
it was like, if you can see here, like you can see this corner of the image that loaded. But if you could see the rest of it, you'd be really impressed. Fortunately, at the end, the like big overview image did show, so we could see a little bit of it.
Yeah. There were some technical difficulties at the conference this year. There was one session where there was a fire alarm going off.
Oh, yeah.
The fire alarm was in a totally different part of the hotel where the conference was, so we were fine. And I don't think there was actually a fire, but the alarm was going on for a while.
Yeah, and they were making announcements like simultaneously to the presenters about like basically just like, hold on, everybody. But you couldn't really hear the announcements.
Yeah.
So it's all going on at the same time.
The presenters did really well because they kept going through it all.
Like a pro.
Yeah. There was a talk about Thescelosaurus. This is by Boyd. And Thescelosaurus, it's a small neo-ornithischian dinosaur. It's from the Late Cretaceous. It looks kind of similar to Hypsilophodon, to give you an idea what the dinosaur looked like. I just want to read a quote real quick from the talk. It was, the only thing rarer than a Thescelosaurus skull is a Thescelosaurus forearm. And this talk was about a forearm.
Dun dun dun.
Yep.
They found the rare piece.
Yes. It's MOR 979, and you can see it's completely covered with this dermal tissue across the bone.
In other words, skin.
Yes. They said there's loose flaps of skin around the right ankle, too, and that's flapped out away from the body. And there you can see the internal surface of the skin instead of the external surface. It's like pulled down and flipped inside out.
But that wasn't even the coolest thing about this find.
Yeah. I just liked their description there. That's why I wanted to pass it on.
The coolest thing is that the radius, or the outer radius, I could say, and so that's like the outer side of the forearm, seemed to have spurs on it, which is really crazy. It kind of reminded me of, I think it was Spicomelus, and potential ankylosaur that had spikes sticking out of its rib. Like, what are these dinosaurs doing with just spikes sticking out of them all over the place? It's like our childhood dinosaurs of like extra spiky weirdos are coming back. So basically, they found a while ago that there was a radius that had some spikes on it, but they weren't sure if it was a taphonomic thing, like during the fossilization process, maybe the bone broke a little bit and sort of splintered out and made these things that looked like spikes. But they just recently got to the other arm and found that it has the same spikes on it, and they look basically the same. So it's like, okay, it wasn't lightning striking twice in the same place. This is an actual anatomical feature of Thescelosaurus. And so they have these spurs on them. They also have a covering that look like they might be keratin. So basically what you've got here is forearms with spikes sticking out of them, like, I don't know, some sort of gauntlet situation going on. But they're not super huge. It's a good analogy to compare them to iguanodon thumbs, where it's not a big enough weapon to really be, definitely not hunting with it, probably not even really defending yourself too much against a large predator, but they were definitely there. So then they were trying to answer the question of what were they using these spikes for. So what they think is that rather than trying to give a animal attacking it a bear hug, which is what would be required in order to actually sort of use these things as a defensive weapon, that they were probably using them for intraspecific combat, for something like competing for a mate.
Very cool. They also found, while they were preparing this specimen, some clues that you can look out for to find more soft tissues in other specimens, in other dinosaur fossils. It's these cemented fractures. They were all sealed back up with the same mineral that was fossilizing the skin itself. In areas with high calcium and low iron, they didn't see those fractures.
So in other words, if you find a fossil that has high iron and low calcium, might be a good spot to look for skin.
Yeah, if you see these cemented fractures too in the field, that might mean, there's soft tissue there. And yes, it's worth collecting that fossil, because sometimes you have to make these hard decisions out in the field on what you can collect and what has to stay there.
Yeah, and a lot of times the rock that has that high iron and low calcium and also has cracks that are sort of re-cemented together are really hard pieces of rock. So people see them and they're like, I don't want to, no one wants to deal with that. It's going to take forever to prepare. It's going to be really difficult.
Yeah.
But if when you get to the center of that Tootsie Pop,
there's soft tissue.
Yeah, then it's totally worth it.
Yeah, there seems to be more work coming out lately that shows, and we've talked about on our podcast, that shows that maybe these soft tissues or these skin impressions, they're not as rare as we thought.
Yeah. Yeah, in this case, it's more than even just an impression. It seems to be the actual skin, which is really cool. And one more detail that they mentioned is there is a Thescelosaurus forelimb out there in the world which doesn't have these spikes on it. And that could be, this comes up all the time, but it could be one of the first pieces of evidence for sexual dimorphism in dinosaurs, because if it is a thing where males, for example, are competing for a female, the female might not have those spikes on their forelimbs. But again,
really hard to tell.
Especially like you said, it's one of the most rare bones to find. So yeah. So keeping going with the soft tissues, we saw a really awesome talk by Henry Tsai. I think we've talked about his work a little bit before in the past, but basically the gist of it is that sauropods have a ton of soft tissues. They have ligaments, cartilage, all over the place. They need a lot of extra padding on their feet, all sorts of stuff. Apatosaurus also has a really big gap between the femur and the top of the hip, which was probably covered with a huge bulge of cartilage on top of the femur.
Yeah.
So you can think about it's relatively flat, but it needed to be round for that socket, and that whole round part was cartilage. Which makes sense. I mean, it needs a lot of cushion for such a large animal moving around. It doesn't want to grind its bones down. So covering that with cartilage, it's sort of almost like a hip replacement on the fly.
Yeah.
So you can just keep replacing the cartilage easier than dealing with bone wearing down.
Less painful that way too.
Yeah. The really interesting thing, and I think this was hinted at before, was the quote unquote sacralization of caudal vertebrae. And so in modern birds, what you see is, for example, in ducks, there's a really long cartilage extension down the base of the tail, and it ossifies, and meaning it turns into basically bone. And as it ossifies, it quote unquote recruits vertebrae into the sacrum. So the sacrum sort of expands as this piece of cartilage is turning into bone. And so it's sacrum, which is that the vertebrae in between the hips, is basically expanding over time, which is useful in birds because they like to have a really stiff body for their flapping their wings and everything working properly. They also pointed out that alligator mississippiensis, the alligator that most Americans are most familiar with, has a similar cartilage down its tail, and that attaches to the caudofemoralis muscle we were talking about earlier. The caudofemoralis is the muscle that goes from the tail to the leg, and it helps lift the leg. And it's a very useful muscle. But in this case, what that means is they can have a much larger caudofemoralis brevis muscle because it has this larger attachment point. Rather than just having to attach to the bones, now it's got this extra large piece of cartilage that it can attach to that sort of acts like where muscle would normally attach to a bone. The cool thing is that different lineages of sauropods have different indications for how much cartilage they had on things like on the top of their femur, like how we think Apatosaurus had that big old bump, but also around the hips. They have indications for different amounts of cartilage on the different sides of the hips. And so that means that some of them would have had potentially this really large chunk of cartilage sticking down the base of the tail for a much larger muscle attachment point there, which is just so cool. And it's like a life hack for getting extra muscle when you don't have enough bone there. Grow this big cartilage structure out.
Was it Diplodocus and Titanosaurs? They might have helped them with their tripod posture.
Oh yeah, that's a whole other feature of it too. Yeah, because it would potentially strengthen the base of the tail there. And there have been thoughts in the past about, did these dinosaurs ever rear up? And with all that weight, a lot of people say, well, you couldn't support all the weight on those two hind legs, but if you can recruit the tail to supporting, and now, it reduces the amount of weight that each leg has to support because the tail is helping, then that could help.
Yeah, also early macronarians, they might have used their hind limbs, their hip joints could work in ways and they were more flexible for kicking.
Oh, yeah. Yeah, exactly. So there's a lot of things that you can figure out when you start looking at the soft tissues or the attachment points on the bones for soft tissue and try to recreate it that you can't tell from the bones alone.
Yeah, and it could give you a lot more insight into behaviors. Really interesting how all these things connect.
I also have just a really quick summary of Lyman's talk. They were looking at how well some different animal groups preserved in the Moreno Formation, which is about 80 million years ago in California. Or at least that's the oldest part of it, and the part that has a lot of the dinosaurs. But there's even more mosasaurs and plesiosaurs in there, but there are about 5 hadrosaurs that have been found in the area.
Nice.
And basically, they were scoring them for completeness and, how broken they were and all that kind of stuff. And what they ended up finding was that the hadrosaurs actually turned out to be the most complete, which was really surprising to me.
That is surprising, especially since there's so few of them.
Yeah. So it does make you wonder, there's only 5 of them compared to, say, 77 mosasaurs. Maybe we're only finding the more complete hadrosaurs, or just by chance, the 5 we have are more complete than the other ones. But even though they are more complete than the plesiosaurs and the mosasaurs, they are a lot more beat up. So there's more abrasion, there's more weathering, there's more fragmentation in the hadrosaurs. But there's still, I always like to hear that there are dinosaurs that are in California because they're rare and it's where we are. So it's nice to know there are dinosaurs around.
Hey, we've got a state dinosaur. That's pretty cool.
Yes. And that state dinosaur is one of these 5 hadrosaurs. Augustinolyphus is from the Moreno Formation. I should also point out there was an interesting question in the Q&A part, which was the question, were there any bite marks on these hadrosaurs? And even though there have been bite marks on other dinosaurs, especially like shark bite marks and things like that in the more aquatic marine settings, there weren't any bite marks on this one. It could be that the sharks from the formation weren't the type to do a lot of scavenging because the only sharks we have from it are known from the deep ocean. But there are sharks everywhere. So it seems like these hadrosaurs managed to escape getting chewed on by sharks.
Interesting. To wrap up our session on soft tissue and taphonomy, Hannahbaum talked about Orodromaeus at Egg Mountain, and that's at the Two Medicine Formation near Choteau in Montana.
Good old Choteau. Got a shout out in Jurassic Park.
Oh yeah, it did.
It's pronounced really weird compared to how it's spelled, so you can see why someone would
We didn't know how to pronounce it correctly until we went there.
Yeah.
And one of the points that I found interesting from this talk was that Egg Mountain, they said, was not a breeding ground. It was more like a nursery.
At least for
Orodromaeus.
Yeah.
Yeah, so Orodromaeus, they seem to hatch somewhere else, and then the parents bring them over for this nursery.
Because we didn't find any eggs, but there are some babies.
Yep. They also found Orodromaeus probably cared for their young up until 2 years of age.
Yeah, so that was based on the amount of basically fossilized babies. Which is, so in other words, The hypothesis is when the parents stop caring for the young, that's when you get thrown to the wolves, more or less.
Or the Tyrannosaurs.
And you're likely to not survive. So with most dinosaurs, there's sort of this bimodal thing where there's a bunch of small ones that die, and then there's a bunch of older ones that die when they get, older and have issues. But with these dinosaurs, we don't have really small fossils. We have a bunch of them that are like 2 years old, though. So their hypothesis is basically, well, the very young ones were getting cared for by the parents, and that's why they survived longer. But then at some point, they got kicked out on their own, and that's when they ended up getting fossilized. However, there's another option for that, and it could be that they're getting fossilized in their burrows, and that happens to be the ages of the ones that are in the burrows. Because there was this really cool experiment done. It's called Experiment 10 by Verricchio and Woodruff back in 2011, and they were looking at Oryctodromeus, where I was talking about our Oryctodromeus burrows.
It's the first burrowing dinosaur we know about.
Yeah, and what they showed is using this experiment that if you have a burrow, if it gets filled with water and sediment in a certain way, you end up with the bones ending up looking a certain way and getting preserved while in that burrow. And these bones happen to look really similar to that. So it's likely, based on that evidence, that Orodromeus was in a burrow similar to Oryctodromeus and that they were fossiling in a similar way. And then on top of that, a lot of the bones from Egg Mountain are in really bad shape, especially like the larger animals, which obviously weren't in burrows unless they had some crazy huge burrows that we haven't found out about. So these bones were in much better shape. So the proposal is, okay, well, they're in better shape because they were in a burrow. They weren't exposed to the weather as, the taphonomy process kicked in and they were slowly turning into fossils. Instead, they were preserved in these burrows and they maintained their higher quality. So yeah, a few different pieces of evidence that they might have been in burrows between the age of the fossil, the quality of the fossil, and their close relationship with Oryctodromeus.
Yeah, I love hearing about burrowing dinosaurs.
Yeah, they are very interesting. There are burrowing birds today as well. I talked about them in some fun fact, I don't know when, a while ago. Burrows are very comforting. I like being in small confined spaces, so I can understand why dinosaurs would like it too.
I like to spread out more, so.
Most people do. And we've got a few more talks about Caenagnathids and then Dinosaur of the Day Caenagnathus. So before we get into that Caenagnath spectacular, we're going to pause for a quick sponsor break. So the first talk we have about Caenagnathids was by Greg Funston, although he wasn't the one that wrote the presentation. It was supposed to be Wilkinson, but they weren't available to do the presentation.
And this is in the theropod session. We'll be covering the rest of the theropod talks in another episode, but just couldn't pass up the opportunity to get into the Caenagnathids.
Yeah. When I saw your Dinosaur of the Day was Caenagnathus, I was like, we just learned a bunch about Caenagnathids. We got to cover them at the same time. So Caenagnathids, I'm sure Sabrina will get more into this, but they're unusual because they have really decorated toothless beaks. They also often have, like head crests and things like that, which are, part of that same keratin type structure. Really interesting looking animals. Unfortunately, our late Cretaceous Caenagnathids are very confusing taxonomically because we don't have a lot of overlapping bones. So it's really hard to compare the different Caenagnathids. Fortunately, the dentaries are pretty common, so that tends to be the part that gets compared, the lower jaw. They're pretty complex, and there's a lot of features of them that have been considered diagnostic. So some of them, for example, turn up sharply at the front, so they have sort of like a pointy upward, almost like a tooth at the end. But again, they're toothless. But
or also known as edentulous.
Yes. And then other ones are pretty flat at the end. This new dinosaur they're talking about was found in Medicine Hat. It's actually not that new. It was from 1991, but newly described. It was farther south than Dinosaur Park Formation. It's closer to Montana. But it has been referred to lots of things over the years. Interestingly, because of some new stratigraphy, it was placed in the Lower Oldman Formation, which made it about 2 million years older than we had previously thought it to be. And we always say the average species lasts roughly 2 million years, which means this one's getting placed sort of out on its own. Partly because of that, it may be a new species, but they also did an analysis of as many of the features on that dentary as they could, and they found even some new spots which seem to be unique on different Caenagnathid's that hadn't been scored before. So they're working on adding in a whole bunch more detail into these comparisons of Caenagnathid's so that they will be able to fully describe this as a new species and hopefully get some more clarity on the other Caenagnathid's as well. We also had an update on Anzu wiley.
Oh, I like Anzu because that was first described in 2014, so it's one of the first dinosaurs we covered on our show.
And I think it was the first dinosaur in our first book, too.
Oh, yeah. Well, because alphabetically.
And it had that nickname, Chicken from Hell, I remember.
Such fond memories.
Yep. So there was a talk by Dave Evans, although, again, this is one where it should have been presented by someone else, but they weren't available. The talk was created by Simon, and they started off pointing out that most Caenagnathid's are from North America, and even further inside that, mostly northern Laramidia, so that's places like Alberta and Montana.
Mm-hmm.
But oviraptorids are all from Asia, so there's this interesting dichotomy.
Oh, I never thought about that before.
Yeah, so even though they're pretty similar overall, there is this bifurcation. Most of them in general are from the Campanian and Maastrichtian, which is the very end of the Cretaceous. But again, we do have a pretty incomplete record of these animals. And because we don't have a lot of body elements, like I was saying, it's a lot of dentaries and things like that, it can be hard to determine if we have adults. Some of them might be juveniles, and then that throws in a whole other problem of whether or not they're unique genera, because if you're only comparing one bone and that bone is changing as the animal grows, you might have several things that you've named different species, but they're all actually just different ages of the same thing.
Mm-hmm.
So if you're trying to figure out if something's an adult, the best way to do it is with histology, which is cutting into the bone and looking for lags. Or if it doesn't have lags, you can still look at details of the bone to see how mature the bone looks. So is it still growing rapidly or not? You can tell that based on the structure of the bone in a lot of cases. So in the past, they found that a Podoraptor is immature and it might be a Haplochirostenodes. But then they're moving on to Anzu to see if Anzu is an adult. And what they found, they cut into the Anzu holotype, and they found that it is, in fact, an adult. But there are 2 additional specimens which have been found that aren't the holotype, just 2 other Anzus.
Oh, yeah. Is it one nicknamed Pearl?
Yes.
I like the nicknames.
Both Pearl and the other unnicknamed one are about 3% larger than the Anzu holotype. But the weird thing is, that holotype has less vascular bone, indicating that it is probably an adult.
It was done growing?
Yeah, pretty much. And on top of that, the lags are starting to pile up rapidly at the outer edge, enough even to consider it an external fundamental system, which is the EFS, which means that it's an adult. That's like the gold standard for finding an adult, if you can, in the histology. And that means that the holotype is as big as that individual would have gotten. However, one of the other individuals, the unnamed one, has an EFS, but the other one, Pearl, has similar vascularization, but there isn't as much remodeling of the bone and there is no EFS. So that one's considered to be a subadult. So what you end up with is that the holotype, which is the smallest of the 3, is an adult. You've got another one that's sort of in between. It's like almost fully an adult. And then you've got one that's clearly a subadult, which is bigger. And I think it's a good reminder that even if we find a dinosaur and it is an adult and it's done growing, that doesn't mean that it's the maximum size of that genus.
Mm-hmm.
We often simplify it by saying like, oh, it's got this EFS or it's got these indicators that it was an adult and therefore that's as big as it would have gotten.
Right.
And that's true for that individual.
I'm an adult. I'm done growing. And I'm like a foot shorter than you, Garrett, who is also an adult done growing.
Exactly. So yeah, there can definitely be a lot more variability in the size of the animals beyond just what you find in a single individual and whether or not it's done growing. And of course, that means Anzu got bigger than the holotype, which was already pretty big. And last but not least, in the Caenagnathid related talks, this one isn't super Caenagnathid related at first glance, but it'll come full circle and you'll see how it's Caenagnathid. So
All right.
It was presented by an undergrad at Carleton University named Tristan Warnock Juto, and I thought they just did an amazing job because it must be intimidating getting up in front of all these world experts when you're basically just starting your studies in terms of how much studying you got to do to be a paleontologist.
Mm-hmm.
So yeah, I was very impressed. Plus, it was just a really cool presentation. So what problem they were trying to solve is we have a ton of isolated theropod toe bones.
Yeah. What do you do with those toe bones?
Yeah. So, I mean, it would be useful, even if you don't have an articulated dinosaur, it's really useful to know what type of animal a bone came from because it tells you what was living in that ecosystem. And with all these isolated toes, it's hard to figure out because we don't have that many complete feet. So you can't just say, okay, this bone is isolated, but it would fit into this complete foot. So we can tell it was this bone of this foot, and you just do a one-to-one comparison. You often end up having to do a lot of interpolation, like, oh, it's about this big, but it has these sort of shape details. So it was probably from this type of animal, and maybe it was this bone in the foot from that animal. They wanted to get a more quantifiable way of doing it. So they use something called elliptic Fourier analysis, or EFA. And basically, it's a Fourier analysis that encloses a closed shape rather than a typical open wave. So if you're familiar with Fourier transforms, you can use them to make like MP3 files and things like that. But basically, it's just a combination of sine waves that are at different amplitudes and frequencies, and then you get a mathematical model of a shape in this case. So the important thing there is that you can actually end up with a mathematical equation for a shape, and that makes it easy to compare. And in this case, what they found was that if there are more harmonics, that allows representing a more complicated shape. That's just in general how these Fourier analyses work. And so if you have a really complicated foot bone, it's going to have more harmonics in it. And then you can look at the other details of the equation to figure out some of the other shape details. So what they did is they took some of these toe bones and they tried to determine what they were from. And interestingly, it's like it could be, for comparison, if you think about people, if you have like a small person and a larger person, you might find a bone and think like, oh, this could be a pinky toe from a large person, or it could be a big toe from a smaller person. They had 3 different theropod groups. They had tyrannosaurs, ornithomimids, and Caenagnathid's. So I told you they'd come up.
There you go.
And so they had all their toes. They found that one of these toes could have been either a tyrannosaurid or an ornithomimid toe, but probably not a Caenagnathid. And that was because overall the Caenagnathid toes tend to be more gracile, and that was especially true for the 3rd and 4th toes. So it was a really interesting comparison because there are a lot of subtle differences in the shape of these bones, and it's hard to tell the difference between a small tyrannosaurid bone versus a similarly sized ornithomimid bone. But by using this type of analysis, it can help you get in the right ballpark of, well, it's probably not a Caenagnathid, so you can not bother looking at all those feet. Whatever complete feet we have of Caenagnathids, not all that many, but forget about those. Focus on the tyrannosaurids and ornithomimids. So it's basically a tool that can be used to sort of get you in the right ballpark of identifying all of these random toe bones we have, which aren't associated with feet, and we really don't know what animal they came from. So sort of a first pass of getting you on the right track. I love anything that helps us figure out what, get through these collections, because we have a lot of unidentified stuff in museum collections around the world.
Yeah.
So I could definitely see this being extremely useful.
Especially the collections of toe bones. And now on to our dinosaur of the day, Caenagnathus, or Caenagnathus. But If you've been listening to this whole episode, we kind of keep defaulting back to Caenagnathus, so that's probably what I'm going to stick with.
Yep.
This was a request from Crow via our Patreon and Discord, so thanks. Caenagnathus was a Caenagnathid oviraptorosaur that lived in the Late Cretaceous in what is now Alberta, Canada, found in the Dinosaur Park Formation. It was large, may have been about as big as Anzu, although now we know Anzu probably got bigger, so...
At least a couple % bigger.
Yeah. It did look similar to Anzu, looked bird-like, with feathers and long legs. It also had a long tail and S-shaped neck, and probably had a crest on its head. It's thought to be around the same size as Anzu because of the known specimens of Anzu and Caenagnathus. The pubes are about the same size, and for reference, Anzu was about 11 feet or 3.5 meters long. At least, this is pre this SVP talk. Anzu, of course, was probably a bit larger. Caenagnathus is estimated to weigh up to 212 pounds or 96 kilograms. It had a long, flattened, toothless lower jaw. As Garrett mentioned, Caenagnathid's all had the toothless jaws. It had a shallow jaw, which is different from other oviraptorosaurs that are more, it's like an upturned beak. And that might mean that Caenagnathus ate more plants. Caenagnathid's in general were probably generalist feeders that ate plants and small animals, maybe eggs. The fossils of Caenagnathus found include lower jaws, a tail vertebra, and bones from the hand and limbs. The type species is Caenagnathus collinsi. The genus name means recent jaw, and the species name is in honor of the late Dr. W.H. Collins, quote, for many years director of the Geological Survey of Canada. Caenagnathus was described by R.M. Sternberg in 1940, and at first it was thought to be a toothless bird. The jaws were found in 1936, and then it was named Caenagnathus, and Sternberg wrote that, quote, the holotype is an admirably preserved lower jaw, complete except for the ventral border of the right ramus.
Admirably preserved.
Yes, I liked that phrasing. That was the main reason I quoted that.
But again, we're just working with the lower jaw.
An admirable lower jaw.
I guess if all you have is a lower jaw, it's nice that it's admirable.
Yeah. The holotype was found in the summer of 1936 by a field party from the National Museum of Canada under the direction of C.M. Sternberg. In 1988, a different specimen that had been in storage since 1923 was rediscovered and studied, and that helped link several fragments of an oviraptorosaur into one dinosaur, Caenagnathus, which we covered in episode 404. There's a lot of debate and subsequent studies finding Caenagnathus and Caenagnathus to be separate. In 2010, Phil Center did a phylogenetic analysis of Coelurosauria and found Caenagnathus and Caenagnathus to definitely be separate, quote, casting doubt on their synonymy. Then more complete Caenagnathid specimens were found in 2014 and 2015, like the discovery of Anzu, and that helped show even more differences in these fragmentary specimens. In 2015, Funston and others re-examined Caenagnathid fossils from Dinosaur Park Formation and found more Caenagnathus collinsi fossils, including a tail vertebra, femur, and parts of the feet. Funston and Curry in 2020 described another Caenagnathus specimen with a lower jaw, and that helps support that Caenagnathus and Caenagnathus are separate. There's some differences in the feet and the toes between them. In 2020, Gregory Funston re-examined Caenagnathid material and re-described Caenagnathus collinsi, and there's some disagreement over the diversity of Caenagnathid's. One of the specimens in the study was at least 12 years old and nearly done growing, so it probably grew quickly at first and then slowed down. In 1993, Phil Curry and others named, in quotes, Caenagnathus sternbergi, based on new specimens found in the Judith River Formation, but a 2014 analysis found that to be a sister taxon. So again, we just have the one and only type species, Caenagnathus collinsi. Now, other dinosaurs that lived around the same time and place as Caenagnathus include ankylosaurs, ceratopsians, ornithopods, pachycephalosaurs, ornithomimids, oviraptorosaurs, paravians, and tyrannosaurs. And other animals, in addition to dinosaurs, that lived around the same time and place include amphibians, crocodilians, lizards, plesiosaurs, pterosaurs, turtles, mammals, and fish. And now for our fun fact, I decided to take a page from Garrett's book and bring it back to Thescelosaurus, since we had a Thescelosaurus SVP talk. Kind of like how you linked your Caenagnathid talks because of our dinosaur of the day.
Yeah. Keep it consistent.
Yeah. This was from a poster session, actually one of the virtual posters. Well, at least it was uploaded to the virtual platform, which is very much appreciated that we had access to additional talks and posters.
Yeah, it's hard to get around and see all the posters at SVP because you only have a couple hours when the people are talking about them and everyone wants to talk to everybody with a cool poster. So yeah, it's difficult.
Yes. But luckily, yeah, we're still actually watching talks and posters over the next few weeks. Now, this one was Liebke and others did bone histology of a specimen of Thescelosaurus. Well, Thescelosaurus caenagnathus. And just as a side fun fact, you can do histology on ribs in addition to limb bones. Sometimes the ribs work out better. There's 3 species of Thescelosaurus, but for this one, they're focusing on Thescelosaurus caenagnathus. Now, no previous histology had been done on Thescelosaurus, but they said it's one of the most common dinosaurs from the Frenchman Formation in Saskatchewan, Canada. The holotype of Thescelosaurus caenagnathus is smaller than other individuals of other Thescelosaurus species, such as Thescelosaurus neglectus. But there is one large specimen that was found in the Frenchman Formation that is similar in size to the Thescelosaurus neglectus specimen. Anyway, in their study, they found that most of the femora that they looked at of Thescelosaurus caenagnathus had no growth marks. Only one femur had faint growth marks, and that was unexpected, so it's possible that it represents a misidentified specimen. All the ribs had growth marks, so they were able to do the histology on the ribs. And they found that the largest specimen of Thescelosaurus caenagnathus from the Frenchman Formation had more growth lines than the Thescelosaurus caenagnathus holotype, and that might mean that that one was older. So, just going back to what you were saying earlier, Garrett, how histology is probably the best way to figure out the age of a particular individual.
Yeah, that's cool.
And that wraps up this episode of I Know Dino. Hopefully you enjoyed our coverage of SVP so far, and if you want bonus coverage, including talks that are about non-dinosaurs.
Yeah, because there are a lot of vertebrates in the paleontological record, not just dinosaurs.
Yes. Then now is a great time to join our community to get access to that bonus content. That's at patreon.com/iknowdino. Thanks again, and until next time.